Hello and welcome to this video for Mechanics of Deformable Solids. We are still in Chapter 6, Torsion. In the previous video, what we did is first to define the internal torque. So we define, if you know the external torque that are applied to a given member, then you can use the method of section to get the internal torque. So this is going to be, the internal torque is going to capture the effect of the moments that are applied, so the effect of the moments or the torque that are applied to a given member. But what we said is also that the thing that matter is not simply the torque, but also the geometry of the shaft. So we are going to have a second quantity, which is the polar moment of inertia, which we defined in the previous video. So if we have the polar moment of inertia, this is going to capture the effect of the geometry. And so if you combine both the effect of the torque as captured by the internal torque and the effect of the geometry, this is what is going to allow us to calculate the shear stress in a beam that is subjected to some torsion. So in this case, the shear stress will depend both on the external torque that are applied and also on the polar moment of inertia, which can potentially also depend on x. And those two things, the geometry and the torque, is what is going to define what is the stress that is undergone by the beam subjected to torsions. And so the way to convert the internal torque and the polar moment of inertia into a shear, this is what is going to be given by the torsion formula, which is going to be a very important formula for this torsion chapter. So now what we are going to do is to derive this torsion formula, so which is going to give us the shear stress of a beam subjected to some torsion. So for this we are going to consider a general case of a shaft like this that is subjected to some external torque. So in this case, so we are going to consider a shaft like this, and again I'm going to draw, just to illustrate the deformation, I'm going to draw an initial grid that would be drawn like this on the surface of this shaft. So that would be before the deformation. This grid would look like this. So this is before the deformation, and then so this beam is going to be subjected to a torque like this, so that after the deformation, this grid that used to be made of small square will now look like something like this. So now what used to be a straight line will now be shifted. So you will have now a shear deformation of the surface of the beam due to this twist deformation. So this is after the torsion deformation. So one thing that will be useful is to find a way to quantify the amount of the deformation. And for this, one thing that we are going to do is to define the twist angle. So to define the twist angle, let's consider that this is going to be, for example, a point A, and this is going to be point B here. Then after the deformation, point B is now going to become this point C, which means that now you will have a twist deformation due to the fact that this before the deformation was a straight line like this, and due to the deformation now the beam is going to be twisted like this. Then one way to characterize the amount of this deformation is to define the twist angle, which we are going to define like this, which is the angle between point B and point C. So this is going to be phi, which we are going to define as the twist angle. So this twist angle can be used to characterize the amount of twisting of the beam, the twist deformation of the beam due to the torque that is applied. So if we look at it, if we look at this beam from the right, so if we look at it like this from the right, now it's going to look like this. So if we look at the portion of the beam from the right, it will look like a circle like this. So you have the point O, the center of the circle like this. We are going to define C, which is the radius of this circle. So initially point B would be here, and after the deformation, so you will have the twist angle phi that will characterize the twist angle from point B to point C after the deformation. So this is going to be the angle. So one quantity that will be useful to define as well is, in addition to this twist angle, another quantity that will be useful is this quantity here, which is the distance, the length of this portion of circle. So in this case, we are going to calculate the distance of this portion of the circle. We are going to call it delta. This is going to be the displacement from point B to point C, the distance between point B to point C, like this distance of the portion of the circle between point B and point C. So in this case, this is going to be a distance. So phi is an angle, and delta is the distance over which point B has been displaced up to point C. So now, let's find a way to, what we are going to do is to relate this twist angle to the distance, and to relate this to the shear strain that this beam is subjected to on its surface. So to define the shear strain, let's look more closely to what happened at the surface of this beam. So for example, if we look more carefully at a portion of this beam on its surface like this, so let's consider initially one of those square like this. Now if I look more carefully at what happened on the surface, initially before the deformation, this surface was covered by some grids like this that used to be normal with respect to each other, orthogonal with respect to each other. There used to be some small square, and after the deformation, then those lines that used to be horizontal will now have a tilt, will have tilted with respect to the horizontal axis. So now it means that you used to have some small square like this that used to be perfectly orthogonal. After the deformation, those small square now becomes like a diamond shape like this. This is after the torsion deformation. So if I want to calculate the shear stress like this, I can use the definition of the shear stress. And the shear stress, the way we define it in the chapter on the shear stress, and we defined it as the angle of this between those two axes here. So if I define this angle theta, I can calculate the shear strain that is subjected that is applied on the surface of this beam. And so this shear strain, by definition of the shear strain, it is exactly equal to this angle theta. The only thing to be careful here is that here you have a deformation like this, which is, when we defined the shear strain, we said that this is a negative shear strain. As a reminder, a positive shear strain is either a deformation that is like this, or a deformation that is like this. This would be a positive shear strain. But in this case, a torsion like this will induce a negative shear strain. So in this case, the shear strain that we define is not equal to theta, but to minus theta. If theta is positive, then that would induce that you would get a negative shear strain. So in this case, a positive torsion with a positive torque will induce a negative shear strain and also a negative shear stress, as we are going to see in the following. So now let's look in more detail at how we can calculate this shear strain. So we said that the shear strain by definition is equal to this angle theta, but we also said that as a simplified expression of the shear strain, which is valid in the case of small angles, it's also fairly equal to the tangent of this angle. And this is because if theta is very small, then tangent theta is almost equal to theta. And this is what is going to allow us to link the twist angle phi to the shear strain by using this approximation that tangent theta is almost equal to theta. So let's do this. So for this, one thing we can do is to look at to look more carefully at what happened at the surface here. So if I now zoom on this surface, so initially you have this line here that goes between point A to point B, and after deformation, point B is being displaced up to point C. So this defines here a rectangle triangle like this, where so you have the angle theta, which is the angle that the new lines that are tilted make with respect to the original horizontal line. So this angle theta, I can find this angle here. And now I also have this distance delta, which is the distance between point B and point C. So distance delta would be here. And then I can also define another quantity, which is the length L of the beam along the longitudinal axis. So length L would be this distance here, this edge of the rectangle triangle. So now based on this, I can express the tangent of theta. So the tangent of theta will be the opposite side, which is delta, divided by the length L. But another thing that I can write is that delta here, delta is the length of this portion of the circle. So the portion of the circle, if I take the entire circle if the twist angle was 2 pi, so if I was covering the entire circle, then the length of this portion of circle, if it was the entire circle, would be 2 pi times the radius. That's the perimeter of the circle. But in this case, since I'm only considering only a portion of this circle, the length of this portion of circle is going to be equal to the radius c times the angle in radians. So again, if this angle was 2 pi, then you would find the usual formula that gives you the perimeter of a circle. But in this case, since it's only a fraction of the circle, the length of this fraction of circle is equal to the radius times the angle and the angle needs to be expressed in radians in this case. So delta is equal to c times phi, radius times the twist angle. So I can replace this in the formula. So it's the distance c, the radius c times the twist angle phi divided by L. So which means that based on this, I can re-express the shear strain based on this expression as minus C5 divided by L. So this expression, minus C5 divided by L, is going to give me the shear strain, but it's so far as the shear strain at the surface. This is the shear strain at the surface of the member. And the shear strain at the surface is the position, the surface is the position at which the shear strain will be the maximum. Why is that? Because again, if I look at it from the right, if I draw the cross section from the right again, so if I look at a point C, this is the radius. So if I look at for a fixed twist angle like this, so here this is the twist angle phi. If I look at the displacement of these points, if I look at the surface, you have a very large displacement. But if I go deeper and deeper within the shaft, and if I go close to the point 0, then this displacement becomes lower and lower. The distance delta becomes lower and lower if I go closer to the distance, if I go closer to the center. So one thing that you can define here is that you can say that at the surface, this is where the shear strain is going to be maximum. So I'm going to write it gamma max because this is at the surface and the gamma is going to be maximum there. And so in this case, gamma max is going to be equal to the expression that we just saw, minus C times phi divided by L. That's at the surface. But now if we look inside this beam, so now if I don't look at the surface, not at the distance C from the center anymore, but if I look at what happens inside the member, then here, if I want to get the expression, all I need to do is simply to replace C by the distance from the center. If I want to see what is the shear strain not at the surface here, that is to say at a distance C from the center, but if I want the shear strain somewhere inside this beam at a distance R from the center, now to get this expression, all I need to do is to replace C by the distance R, but the expression otherwise remains the same. So now I have a second expression that gives me the shear strain not on the surface but somewhere inside the shaft. So one thing that is useful to do for the following is now to combine those two expressions. So what you can do is to combine those two expressions to say, for example, if you divide those two expressions, you can say that if you take the shear strain, you take expression 1 and you divide it by expression 2. So you take the shear strain inside the material divided by the maximum shear strain at the surface. So if I do this, the terms phi and terms L disappear and the minus sign gets cancelled out. So if I do this, all I get is the ratio between R, the distance from the center, and C, which is the radius of the center. So that gives me a simplified expression because now I can write that the shear strain inside the member, the shear strain gamma at a given distance R from the center, is equal to the maximum shear strain gamma max times R divided by C, where R is the distance from the center at the point at which you want to calculate the shear strain, and C is the radius of this of the cross section of the circle that defines the cross section of this beam. So this gives me a simplified formula to express the shear strain within a member subjected to torsion. So now I have the shear strain within the beam subjected to torsion, but what I want is the shear stress to estimate the risk of fracture. So for this, what you can do is to use the Hooke's law, because the Hooke's law is what is converting shear strain into shear stress or vice versa. So here we're going to use the Hooke's law. The Hooke's law tells us that the shear stress is related, is proportional to the shear strain, and the proportionality constant is the shear modulus G. So if we apply the Hooke's law at the surface of the beam, the Hooke's law tells us that if you take the shear strain at the surface of the beam, so at the surface this is where the shear strain is maximum, it's equal to gamma max. Since the shear strain is maximum, that is also going to give me a maximum shear stress. And the formula is that the shear stress, tau max, is going to be equal to gamma max times the shear modulus G. So this is at the surface. Now, if we apply the same formula but inside the beam, now that's the same thing. You have the shear strain inside the beam. If you want the shear stress, you need to multiply it by the shear modulus G. So now again, I can take those two expressions 1 and 2 and divide them with respect to each other. So if I take 1 divided by 2, I have now tau divided by tau max, so the shear stress inside the material. So this is at a distance R from the center. inside the material, and the other one is at the surface, that is to say at a distance c from the center. The distance c would be the surface, since c is the radius of this circle. So if I take those two expressions and divide them with each other, then the shear modulus G disappears, and in this case, tau divided by tau max is going to be equal to gamma divided by gamma max. And in this case, since we saw that gamma divided by gamma max is equal to R divided by C, then this term is also going to be equal to R divided by C. And so this gives, again, a simplified formula that tells you that the shear stress tau at a given distance R from the center is equal to the maximum shear stress tau max at the surface of the beam times R divided by C. So this gives an expression that tells you, like, if you know the shear stress at the surface, then you can calculate the shear stress inside. So just one thing to check that this formula is correct is that if you want to check what this formula would give you for the surface, so if you actually look at the surface, that is to say for R equals C, if you transform R into C, where C is the radius of the circle, so if you look at the surface, then what you get is that tau max equal tau max. That is to say the shear stress at the surface is equal to tau max as expected. The other thing that this formula tells you is that if you take R equals 0, that is to say exactly at the center of the beam, then there would be no shear stress and no shear strain. The shear stress and the shear strain would be both 0 for R equals 0, that is to say exactly at the center of the beam. And then in between those two cases, between R equals 0 and R equals C, what we find is that the shear stress is increasing linearly with the distance from the center. So now I have this expression, tau equal tau max times R equals C. So this allows me, if I know the maximum shear stress at the surface, then I can calculate the shear stress inside the beam at a given distance R from the center of the beam. But so far, it still doesn't answer the question because we still don't know how to calculate tau max, how to calculate the maximum shear stress at the surface. And if we want to calculate this, we need to convert this. We need to find a way to calculate this shear stress, tau max, as a function of the internal torque that is undergone within this beam. So now what we are going to do is to see how this shear stress can be connected and expressed in terms of the internal torque T that is within this beam. So for this, let's consider what happens when you take a section within a shaft. If you cut a shaft into two parts and then you look at what is the origin of the torque, what is the origin of the internal torque, so the torque applied by the right to the left or the left to the right. So for this, let me take a look at a given cross section. So this is going to be a given cross section. So at a given position X, if I take a beam and cut it at a given position M, so this is in this case the beam would go like this. So somewhere for example, the beam would be attached here to a fixed support, and then so at a given point X at which you are cutting this shaft, then I would take a section here and isolate only the left part. So here I cut this beam at the position X and I only isolate the left between X equals 0 to the specific X at which I am cutting this beam. So now if I take this portion of the beam, the torque that will be applied by the right to the left will be the internal torque. So if I draw it, the internal torque would be like this. I'm going to define the internal torque with the positive sign convention. So this is the internal torque, the torque applied by the right to the left at the position X. So this is the torque, the internal torque at the position X. So now if I try to understand like what is the origin of this torque, if you look at this this section of the beam, the reason that the right part of the beam is creating a torque on the left part is because if you take at each point M of the surface, at each point M within this surface, if you take a small portion of this beam here, if you take a small portion of this of the surface here, the reason that there is a torque that is transmitted by the right to the left is because at each small portion of this surface, at each infinitesimal surface, you will have a force that is transmitted by the right to the left. And in this case, the force is going to be a normal force, it's going to be a shear force, a force that is applied within the surface over which it is applied. So in that case, there is no normal force because the length of the beam doesn't change. So there is no normal force that would either elongate or compress this beam, but you have a shear force. So if I draw another small infinitesimal section here, you would have another small force like this. If I draw another force here, you will have another surface here, you will have a small force like this, and etc. So for every small element of the surface at which I am cutting at the position X, if you look at every small element of the surface, the reason that there is a torque that is transmitted by the right to the left is because at each position of the beam, you have this small shear force that is transmitted by the right to the left. And the contribution of all those small shear force, which I can write dV, will be creating the torque. It's the combination of all those shear force that is going to be responsible of the twisting of the left part of this beam here. So now what is the value of this small shear force? Well, the shear force is related to the shear strain that we just calculated. So what we just said before is that if I take a small element on the surface, so we said that this is going to be subjected to a shear strain. In this case, since this is on the surface, that would be the maximum shear stress, tau max. So you have a shear strain and a shear stress that is applied within this beam, and we just calculated this. So here in this case, due to the fact that if you take like a small cube like this, so if you imagine a small cube, you have this small force that is applied like this on the surface. So this small cube will be experiencing a shear strain and a shear stress, and we can relate the shear stress to this small force dV by using the definition of the shear stress. So in this case, if you take this small cube here, so let's express the shear stress that is applied to this cube. So for this, I'm going to define dA, the small infinitesimal surface around the point that I'm considering here. So by definition of the shear stress, the shear stress would be the force dV divided by the area over which it is applied dA. The only difference here is that, again, this would be a negative shear stress in this case. The sign convention would be negative because in this case, if you look at it from the side here, in this case you have dV that is applied on the right, which would be in this case a negative shear stress. As a reminder, what we call the positive shear stress is exactly the opposite sign convention. So in this case, again, a positive torsion will result into a negative shear stress. So in this case, I can apply the formula for the shear stress. It's force divided by the surface over which it is applied. So it's going to be minus the small force dV. It's a small force dV because it's applied over a very small surface dA. So that's going to be an infinitesimal force. So now let's consider. So we have those small force dV. They are related to the shear stress, tau. So now let's see, how is this force dV going to create a torque? How is this force dV going to create a moment that is going to be transmitted by the right part to the left part of this beam? The reason that you are going to have a torque being created is because this small force dV is creating a moment about the point O. So I can calculate now the small moment associated to the force dV. So each force dV is going to create a small moment about the center O. And so this small moment, I'm going to write it dm. And so the small moment created by dV is going to be equal to, so the force dV times the arm of the force, which is the distance r from the center. That is the arm of the force about the point O. So now if I rewrite this, so the small moment dm created by dv, so this is equal to dv times r. I can replace dv by minus tau times dA using this expression here times r. And what I can also do is to replace tau by its expression. Tau is equal to tau max times r divided by c. So I can rewrite this small moment like this. I can say that this is equal to tau max. So I'm going to replace tau by its expression. So it's tau max, it's minus tau max times r divided by c. So if I rewrite everything, so you have an r square divided by c times the infinitesimal surface dA. So that's going to be the expression of the small moment by simply replacing this shear strain here by this expression here. So now, if I want to get the total torque T at the position X, the torque is going to be the combination of all those small moments dm. So if I want the total internal torque at the point M, at the point X, so I want to see the total torque. So the total torque is going to be the combination, the sum of all those small moment dm. So if I take all those small moment dm created by all the small forces dv and I sum them all over the entire cross section A, then I'm gonna get the total torque. So here, if I want to relate the torque to the shear stress, what I can do is to use this expression. So I'm going to say that, so the total torque is the sum of all the small moments dm. So I'm going to take this sum. So I'm going to replace dm by its expression. So it's minus tau max r squared divided by c dA. And then you need to sum this over the entire cross section. So now let's look in more detail at what is constant within this integral and what can be taken out of the integral and what is not constant and cannot be taken out of the integral. So in this case, tau max, this is the maximum shear stress. The maximum shear stress is the stress at the surface. So it doesn't depend on the position on the cross section. It's only at the surface. So it means that I can take it out of the integral. Then you have c. c is the radius. So again, the radius doesn't depend on the position of where the point M is when I do this, when I calculate this integral over the entire cross section. C is just the radius of the circle. So it's a constant, can be taken out of the integral. On the other hand, r is the distance between the point M to the center. So this distance r cannot be taken out of the integral. It depends on where is the point M within this surface in this integral. So if I rewrite this, it means that the internal torque to T of x is equal to minus tau max. So because this tau max can be taken out of the integral, divided by c, this also can be taken out of the integral, times the integral over the surface of r squared dA. So now if we look at this in more details, here we recognize something we defined in the previous video, which is that the integral over r squared dA, this is the polar moment of inertia. So this is why we define the polar moment of inertia, because this polar moment of inertia is the geometrical quantity that naturally shows up when we calculate the shear stress within a member subjected to torque. So this is why it's useful to define this polar moment of inertia. So now if we summarize everything, it means that now we have an expression to calculate the shear stress. We can write that the internal torque is equal to minus tau max times the moment of inertia J divided by C. Or, so if what we want is to calculate tau max, the shear stress. So tau max, the maximum shear stress at the surface, is going to be equal to minus C times the internal torque divided by the polar moment of inertia J. So this is this expression. This is the shear, this is the torsion formula. So this is the formula that gives you the shear stress at the surface of a member that is subjected to a torsion. So in this case, in this expression, C is the radius of the circle, the distance at which you want to calculate, the distance of the point from the center at which you want to calculate the shear stress, which in this case is the radius, since this is the shear stress at the surface. T of x, this is the internal torque at the point x, and J is the polar moment of inertia. This gives you the shear stress, the maximum shear stress at the surface. If you want the shear stress not at the surface but inside, then you can use this formula here. And so you can replace, you can take this expression, multiply it by R divided by C to get tau, which is going to be now the shear stress inside the member. And in this case, this is going to be equal to minus R times the internal torque divided by the polar moment of inertia. So now you get the formula that gives you the internal shear stress within this member. Now this is going to be not at the surface, but inside the member when you look at a given distance r from the center. So let's look a little bit more detail at this torsion formula that allows you to calculate the shear stress. So in this case, if I look at this formula for the shear stress at the surface, usually we want to apply this formula to find the shear stress at the surface, because at the surface this is where the shear stress is maximum. And so usually we want to find if the shear stress is going to be high enough for the material to break. So if the material is going to break, it's going to break at the point where the shear stress is maximum. And so in this case, that's always going to be at the surface. If the shear stress at the surface exceeds the ultimate stress, then the material will break. And if the shear stress at the surface does not exceed the ultimate stress, then the material is not going to break, because everywhere inside the member, the shear stress is going to be lower than the shear stress at the surface, since the shear stress is maximum at the surface. So let's look at the units first. So the torque is a moment, so it's going to be in Newton per meter. Then you have the radius, that's in meter, and then you have the polar moment of inertia, that's it in meter to the power 4. So if you combine this, you find that indeed you get something that has the unit of a stress for tau, which is in Newton per square meter. The other thing is to look at the sign. So if you look at the sign here, if you have a positive torque, so if the internal torque is positive, then due to the fact that the polar moment of inertia and the circle, the radius of the circle are always positive, due to this minus sign here, it means that a positive torque will induce a negative shear stress. So a negative shear stress will be the consequence of a positive torque. So if you take a beam like this and if you subject it to a positive torque like this, then this beam is going to be deformed like this. And as we said, this is a negative shear stress by Einstein convention. On the other hand, if you have a beam like this and now you subject it to a negative torque like this, then this beam is going to be twisted like this, and now this would be a positive shear stress. So a positive torque will result into a negative shear stress. On the other hand, a negative torque would induce a positive shear stress. So the sign of the torque is opposite to the sign of the shear stress. So that's something to keep in mind. And then the last thing we can discuss is the meaning of this formula. So what we find here is that the shear stress is proportional to the radius, proportional to c, and that's because, again, the shear stress becomes larger and larger as you go far away from the center. So if the further the radius increases, the further you go away from the center, the larger will be the shear stress. So the shear stress is increasing proportionally to the distance c from the center to the radius, proportional to the radius of the circle. We also find that the shear stress is proportional to the torque, so proportional to T of x. So this makes sense. The higher the torque, the higher the shear stress. And we find that the shear stress is inversely proportional to the polar moment of inertia. So in the same way that the normal stress during axial load is inversely proportional to the area of the cross-section here, it means that if you have a torque, if you have a beam with a small polar moment of inertia, then it will have a high normal stress, a high shear stress. But on the other hand, if you have a beam like this with a high polar moment of inertia, if this beam here has a high polar moment of inertia, then it will tend to induce a pretty low stress, because when you calculate the stress is inversely proportional to the polar moment of inertia. So the larger the polar moment of inertia, the lower the shaft will be. So that's why it's always preferable to have a shaft like this with a low polar moment, a high polar moment of inertia, so that you create a low shear stress. So in this case, that would be a low shear stress tau, due to the fact that the polar moment of inertia of this shaft is high. And if the stress tau is lower, then it means that you will have a lower risk of fracture, even if this beam is made of the same material. So a lower shear stress means a lower risk of fracture. So this torsion formula is very important, because this is a formula that you will use whenever you want to calculate the shear stress. To calculate the risk of fracture of a beam subjected to torsion, you will need to first calculate T, the internal torque at each point x. So this is going to be given by the method of sections. And once you have applied the method of section to get the internal torque, then you will use the torsion formula to calculate the shear stress. Be careful that here potentially all those quantities can depend on x. The radius of the cross-section can depend on x if the cross-section doesn't have a constant radius. And the polar moment of inertia also can depend on x. So all those quantities can potentially depend on x.